Welcome back. Last time we turned the derivative into a problem-solving language with optimization. Today we add one more tool to the kit, arguably the single most used trick in Calculus 1, and we attach a story to it that involves a French nobleman, a Swiss mathematician, and what may be the most successful piece of academic plagiarism in history, L'Hôpital's rule. The setup is simple. Sometimes you take a limit and substitution gives you nonsense, 0 over 0 or infinity over infinity. These are the indeterminate forms. L'Hôpital's rule says, in those cases, differentiate the top and the bottom separately and try the limit again. Often you get a number on the first attempt. Sometimes you need to apply the rule twice or 3 times. We'll state the rule, prove it with Cauchy's mean value theorem, work 3 classic examples, and then tell the priority story, which is a much better story than most textbooks bother to mention. Let's start with what an indeterminate form actually is, because it's a phrase that gets thrown around and not always defined. Take the limit of sine of x over x as x approaches 0. If you plug in x equals 0, you get sine of 0 over 0, which is 0 over 0. That is not a number. The symbol 0 over 0 doesn't mean anything by itself. It's a warning sign. It tells you that the limit might exist, or might not, and that the ordinary algebra of substitution has failed. Why is it a warning sign rather than a value? Because 3 different ratios that all give the form 0 over 0 can give 3 completely different answers. The limit of x over x as x goes to 0 is 1. Top and bottom shrink at the same rate. The limit of x squared over x as x goes to 0 is 0. The top shrinks faster. The limit of x over x squared as x goes to 0 blows up. The bottom shrinks faster. Same form, 3 answers. That's what indeterminate means. The form doesn't determine the answer. You have to look at the rates. L'Hôpital's rule handles 2 indeterminate forms directly, 0 over 0 and infinity over infinity. Those are the headline cases. But there are 5 more indeterminate forms that show up regularly, and every one of them can be converted to a 0 over 0 or infinity over infinity with a little algebra. First, 0 times infinity. If f goes to 0 and g goes to infinity, then f times g is indeterminate. Rewrite f times g as f over 1 over g. Now the top goes to 0 and the bottom goes to 0. It's a 0 over 0 form. Apply L'Hôpital. Second, infinity minus infinity. Big number minus another big number could be anything. Find a common denominator or otherwise combine into a single fraction, and you'll typically get 0 over 0. Third, fourth, fifth, the 3 exponential forms, 1 to the infinity, 0 to the 0, infinity to the 0. These all come up in limits like the definition of e, or x to the x as x goes to 0. The trick is to take the natural log first. If y equals f to the g, then the natural log of y equals g times the natural log of f. Now you have a product, which is a 0 times infinity, which converts to 0 over 0. Solve for the natural log of y, then exponentiate to recover y. Long story short, every indeterminate form reduces to L'Hôpital's 2 headline cases. The theorem. Suppose f and g are both differentiable on some open interval containing a, except maybe at the point a itself, and that g' is non-zero on that interval except possibly at a. Suppose further that the limits of f and g as x approaches a are both 0, or both are plus or minus infinity. And finally, suppose the limit of f' over g' as x approaches a exists, or is plus or minus infinity. Then, the limit of f over g equals the limit of f' over g'. That's the rule. Note what it doesn't say. It does not say the derivative of the quotient. It says the quotient of the derivatives. We do not apply the quotient rule. We differentiate the numerator on its own, and we differentiate the denominator on its own, and we form a new fraction. The rule also works for limits at infinity and for one-sided limits with appropriately modified hypotheses. The heavy lifting in the statement is that the input has to be an indeterminate form. If substitution already gives you a number, like the limit as x approaches 1 of 1 over x, which is just 1, you don't apply L'Hôpital, you just write down the answer. Why does the rule work? The proof rests on a cousin of the mean value theorem called the Cauchy generalized mean value theorem. Recall the ordinary mean value theorem. For a continuous differentiable function on the interval from a to b, there's some point c in between where the derivative equals the average slope, f of b minus f of a, over b minus a. Cauchy's version replaces the denominator b minus a with g of b minus g of a for a second function g. The conclusion: there's a c where the ratio of function changes equals the ratio of derivatives. F of b minus f of a over g of b minus g of a equals f prime of c over g prime of c. Ordinary mean value theorem is the special case where g of x equals x. Now the proof of L'Hôpital for the 0 over 0 case. Since f and g both go to 0 at a, extend them continuously by defining f of a and g of a both equal to 0. Apply Cauchy mean value theorem on the interval from a to x f of x over g of x, which equals f of x minus f of a over g of x minus g of a equals f prime of c over g prime of c for some c between a and x. As x approaches a, the point C is squeezed toward a 2. So the limit of f over g equals the limit of f prime over g prime evaluated along the squeezed sequence. Done. The infinity over infinity case is more delicate. It needs a trickier argument because you can't just plug in 0, but the conclusion is the same. Picture for intuition. Two curves, f and g, both approaching 0 at the point x equals a. The blue curve has a steep slope coming in. The red curve has a shallow slope. Near a, each function is well approximated by its tangent line. That's the local linearization from episode 10. So f of x is approximately f prime of a times the quantity x minus a, and g of x is approximately g prime of a times the quantity x minus a. The ratio f of x over g of x is then f prime of a times the quantity x minus a over g prime of a times the quantity x minus a. The x minus a cancels, leaving f prime of a over g prime of a. That's the heuristic. When both functions approach 0, the ratio of their values approaches the ratio of their slopes. L'Hopital's rule promotes that heuristic into a theorem. First example. The granddaddy of all indeterminate limits, sine of x over x as x approaches 0. Check the form. Sine of 0 is 0, and the denominator is 0. We have a 0 over 0 form. L'Hopital applies. Differentiate top and bottom separately. The derivative of sine of x is cosine of x. The derivative of x is 1. So the new limit is cosine of x over 1 as x approaches 0, which is cosine of 0 divided by 1, which is 1 over 1, which is 1. The limit is 1. Now, a small warning. We already knew this limit equals 1 because we used the squeeze theorem to prove it back in episode 7, and then we used that result to compute the derivative of sine of x. If you derive the limit by L'Hopital and then claim the derivative of sine from the limit, you're going in a circle. The rule gives the right answer, but it doesn't constitute an independent proof. As a computation, however, it's instant. Second example. The limit of e to the x minus 1 minus x all over x squared as x approaches 0. Check the form. Top, e to the 0 minus 1 minus 0, which is 1 minus 1 minus 0, which is 0. Bottom, 0 squared, which is 0. Indeterminate 0 over 0. Apply L'Hopital. Differentiate the top. The derivative of e to the x is e to the x. The derivative of minus 1 is 0. The derivative of minus x is minus 1. So the top becomes e to the x minus 1. Differentiate the bottom. The derivative of x squared is 2x. New limit, e to the x minus 1 over 2x as x approaches 0. Check the form again. Top, e to the 0 minus 1, which is 0. Bottom, 2 times 0, which is 0. Still 0 over 0. We can apply L'Hopital again. Differentiate top, e to the x. Differentiate bottom, 2. New limit, e to the x over 2 as x approaches 0, which is e to the 0 over 2, which is 1/2. So the original limit is 1/2. The lesson, you can apply L'Hopital repeatedly, but you must recheck the form at each step. If the form becomes determinate, like a number over a non-zero number, stop and substitute. If you keep applying L'Hopital when the form is no longer indeterminate, you'll get a wrong answer. Third example. The limit of the natural log of x over x as x approaches infinity. Check the form. The natural log goes to infinity. The denominator x goes to infinity. We have infinity over infinity, indeterminate. L'Hopital applies. Differentiate top, derivative of the natural log of x is 1 over x. Differentiate bottom, derivative of x is 1. New limit, 1 over x over 1, which is just 1 over x. As x approaches infinity, 1 over x approaches 0. Done. The limit is 0. Now, the interpretation is more important than the calculation. What we've shown is that the natural log of x grows much slower than x. In fact, the natural log of x grows slower than any positive power of x, even x to the 1000th. You can prove this with the same kind of argument. The natural log of x over x to the p has L'Hopital derivative 1 over x over p times x to the p minus 1, which equals 1 over p times x to the p, which goes to 0 for any positive p. There's a hierarchy of growth at infinity. Logarithms grow slowest, powers grow faster, exponentials grow fastest. The natural log of x is much less than x to the p, which is much less than e to the x. L'Hopital is the tool that makes that hierarchy rigorous. Now for the part the textbooks usually skip, the story of who actually proved the rule. The cast. Johann Bernoulli, Swiss, born 1667, younger brother of Jakob Bernoulli, also a mathematician, father of Daniel Bernoulli, also a mathematician. Founding member of the Bernoulli dynasty, by my count, 8 mathematicians in 3 generations. Johann is the most prolific. He's a student of Leibniz's new calculus, which, at the time, is the new thing, just a few years old. The other player, Guillaume François Antoine de L'Hopital, Marquis de Saint-Aimé, born 1661, wealthy French nobleman. Amateur mathematician, but a serious amateur. Talented enough to understand the new calculus, but not necessarily talented enough to do original research in it. In 1691, L'Hôpital and Bernoulli meet in Paris. L'Hôpital is hungry to learn the new calculus. Bernoulli is happy to teach for money. They strike a deal, a formal written contract which has survived. L'Hôpital pays Bernoulli a generous annual salary. In exchange, Bernoulli sends L'Hôpital his latest mathematical discoveries in regular letters, and L'Hôpital acquires the right to use those discoveries as he pleases. Around 1694, Bernoulli proves what we now call L'Hôpital's rule. He sends it to L'Hôpital in a letter. In 1696, L'Hôpital publishes a book. The title in English, Analysis of the Infinitely Small for the Understanding of Curved Lines. It is the world's first calculus textbook. It is comprehensive, well-organized, beautifully written, and mostly assembled from material L'Hôpital had learned from Bernoulli. The rule we now call L'Hôpital's rule appears in Chapter 9. L'Hôpital includes a polite preface acknowledging his debts to Leibniz and the Messieurs Bernoulli for various things, but he doesn't single out particular results, and readers naturally assume the contents are L'Hôpital's own. The book is a hit. For nearly 100 years, it is the standard calculus text in Europe. The rule becomes known as L'Hôpital's rule, and the name sticks. In 1704, L'Hôpital dies. Bernoulli, no longer bound by the contract, starts publicly claiming credit. He writes letters. He gives lectures. He says, in effect, look, I taught him that. That's my result. Almost nobody believes him. Bernoulli has a reputation as a difficult, jealous, and occasionally dishonest person. He had also, by this point, gotten into a bitter priority fight with his own brother Jakob over the Brachistochrony. So when Johann claims credit for L'Hôpital's rule, the mathematical community shrugs. Bernoulli spends the rest of his life fuming and dies in 1748 still mostly uncredited. Fast forward to 1922. A historian rediscovers the original letters between Bernoulli and L'Hôpital in the Basel archives. The letters include the proof of the rule, sent from Bernoulli to L'Hôpital years before the 1696 book. Bernoulli's claim is conclusively verified. He was right. He proved the rule. He taught it to L'Hôpital, who paid for the right to use it and used it in his book without specific credit. By 1922, of course, the name has been L'Hôpital's rule for 226 years. It's still called that today. So, was it plagiarism? The modern view is nuanced. Legally, no. The contract was explicit. L'Hôpital paid Bernoulli a salary in exchange for the right to use Bernoulli's results. Both parties signed. Bernoulli got what he agreed to. There's no fraud. Ethically, it's murkier. L'Hôpital's acknowledgement was vague enough that readers couldn't tell which results were original to him and which were not. By the standards of modern academic publishing, you'd be expected to attribute specific results to specific people. By the standards of 1696, attribution norms were much looser. Historically, naming conventions in mathematics are a mess. Pythagoras didn't discover the Pythagorean theorem. The Babylonians had it 1,000 years earlier. Pascal's triangle was known in China and Persia centuries before Pascal. The name attached to a theorem is usually the name of whoever popularized it, not whoever first proved it. By that standard, L'Hôpital is a reasonable namesake. He's the one who put the rule into wide circulation. The honest compromise is, call it L'Hôpital's rule out of historical inertia, but remember who actually proved it. Bernoulli. Pitfalls. 5 of them. First, don't apply L'Hôpital when the form isn't indeterminate. The limit of 1 over x as x approaches 0 is plus or minus infinity depending on which side. It's not 0 over 0, it's not infinity over infinity, it's determinate. If you blindly apply L'Hôpital, you'll get the derivative of 1 over the derivative of x, which is 0 over 1, which is 0, wrong answer. Check the form before applying. Second, do not. I cannot say this strongly enough. Do not use the quotient rule. L'Hôpital tells you to differentiate the numerator and denominator separately, not to differentiate the whole fraction. Third, after one application, check the form again. If you got a number, substitute and stop. If you still have an indeterminate form, apply again. But don't apply mechanically without checking. Fourth, the other 5 indeterminate forms. 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, infinity to the 0, need to be rewritten as 0 over 0 or infinity over infinity before you can use L'Hôpital. Take the natural log, common denominator, whatever it takes. Fifth, and most technical, the rule requires the limit of f prime over g prime to exist. If that limit doesn't exist, for instance, if it oscillates, L'Hôpital's rule fails to apply. That doesn't mean the original limit doesn't exist, it just means L'Hôpital can't tell you about it. You need another method. Where we landed. Indeterminate forms are limits where substitution gives a meaningless expression, 0 over 0, infinity over infinity, and 5 others convertible to those by algebra. L'Hôpital's rule says if the limit is of one of the 2 headline indeterminate forms, and the derivatives exist with g prime non-zero, and the limit of f prime over g prime exists, then the original limit equals that derivative limit. The rule is proved by Cauchy's generalized mean value theorem, which says the ratio of function changes equals the ratio of derivative values at some in-between point. 3 examples nailed down the technique. Sine of x over x goes to 1. by L'Hôpital instantly, modulo the worry that we used the same limit to prove the derivative of sine. E to the x minus 1 minus x over x squared goes to 1/2 by applying L'Hôpital twice. The natural log of x over x goes to 0 at infinity, which generalizes to the growth hierarchy. Logarithms grow slower than any power, and powers grow slower than any exponential. Pitfalls: don't apply when determinate, don't use the quotient rule, always recheck the form. And the history: Johann Bernoulli proved the rule around 1694. Guillaume de L'Hôpital published it in 1696 in the world's first calculus textbook, with acknowledgement but not specific credit. The name stuck. The original letters, rediscovered in 1922, confirmed Bernoulli was right, but he had been dead 174 years. Next time, episode 15, Newton's method. A root-finding algorithm so fast that the number of correct digits doubles at every step. See you then. L'Hôpital's rule is calculus eating its own tail. A limit you couldn't evaluate becomes a limit of derivatives, which are themselves defined as limits. Somehow it works, because Cauchy's generalized mean value theorem says the ratio of function values matches the ratio of derivative values somewhere in between. 3 centuries later, we still use the rule daily, and we still call it by the wrong name. If you enjoyed the history, the like button is right there. Press it for Bernoulli. If you got something out of this, please like the video, drop a comment with what clicked for you, or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching, see you in the next one.